Okay, it's 5:30, so let's go ahead and get started today. Good evening, everybody. How's everybody doing today? Did everyone have a good Thanksgiving holiday? Good, great, great. Yeah, so we're no, okay. Oh man, but busy with schoolwork or? Oh man, oh dang. Well, hopefully you're feeling better, and hopefully everyone in your household is feeling okay too. Yeah, oh, okay, that's good. That's good. But yeah, definitely stay safe. I think definitely cases are surging right now, so definitely need to be careful out there. Okay, so we're in the final stretch for this class. We're in the final 2 weeks, and so kind of just like I mentioned before kind of before Thanksgiving. For the rest of this class, we're mostly just going to be doing kind of more practical implementations of finite elements. So we did all the heavy theoretical stuff. So that's what you guys were tested on the midterm before the break. And then you have your project, or you're gonna have to implement the code too. And so from here on out, it's just gonna be practical stuff. So for today, I'm gonna finish up the lecture notes on verification and validation. And then I'm going to do, another kind of quick overview of element types in 3D. So basically, we're going through a lot of the practical decisions that you have to make, when you're using a commercial software like ANSYS, or even when you're using your own software as well. Right? And then on Wednesday, we're going to have another ANSYS activity. But since I want you guys to focus just on doing the project, the Wednesday ANSYS activity, you're not going to have to turn anything in from that. So there's going to be no more assignments to turn in, because I know the project's going to take a lot of work. And so I want to give you guys, the not only the time, but also kind of the mental capacity to work on that. So Wednesday will be more of an ANSYS demonstration, I guess you can say. And so we'll walk through an activity together, just because I think it's really important for you to know how to do beam and shell elements, because that's a really important skill for ANSYS. But you won't have to turn anything in. So the only thing you'll have to worry about in this class in terms of deliverables is just the final project, the code, and also the report. Okay. And then next week will be similar stuff. So we'll go over some more practical stuff, and I want to save some time in class next week to help you guys out with the project if you need that as well. So a few people have already asked me some questions over Thanksgiving about the project, but probably I know probably this week and next week is when a lot of you guys are probably going to get going with it. So I do want to save some time next week to help you guys out with that during the lecture. Okay. And so one other thing I did over the Thanksgiving break was I graded your second midterm. So your grade should be up for that on Canvas. Now that I mentioned that, I don't think I posted solutions yet, so I still need to do that. Right? Question. So this question is that any special office hours this week for private Zoom meetings? Yeah, I mean, if you want to have a private Zoom meeting to talk about the project or anything else, just shoot me an email or shoot me a message on Discord, and we can set up a time to chat. So I'm pretty free this week actually, because I was able to get ahead on my work on Thanksgiving. So yeah, just shoot me an email, shoot me a Discord, and we can set up a meeting. Yeah. Okay. So the average on the midterm was about 40.83 out of 50. Okay. So it was a good average. Right? So it was a long exam. I know it was pretty tough. There was a lot of calculations on that, but you guys did really well. So I was really happy with that. Okay. And so now that we're at this point in the class, and things might change depending on the final project, but I was looking at kind of the overall grades for everyone. And based on that, I don't think there will be any kind of scaling or any kind of curving of the final grades. So, where you sit right now in terms of your final, your overall grade in the class, that's kind of where you can expect to sit, if nothing really changes with the final project. But with that said, the final project is worth 50%, so that's a huge percentage of your grade. So a lot of things can still shift around, but unless something drastic really happens, I don't anticipate that I would adjust the grades. I would just kind of put them in exactly as they are. Okay. Okay. Are there any questions on any of this stuff? Okay. All right. Oh, question. Right, question. So no more homework due. So right. So there's going to be no more homework due. So I want you guys to just focus on the project because it's going to be, it's a lot of coding. And I know the final report's going to take a lot of writing too. And I know a lot of you guys have different, you have other classes or research, that you guys are working on too. So I don't want to overburden you with, so much stuff at the last minute. So, we'll probably do at least one. Maybe I'll do another ANSYS demonstration next week. Depending, I have to take a look on kind of, how we want to spend next week. But then there's going to be nothing more due except for the final project. Due date for the project. So the due date for the project, I believe we set to be the Monday after finals week. And so finals week starts on the 14th. And so the final project is going to be due December 21st. Yes, December 21st at 11:59 p.m. So by that time, you need to turn in your codes for all three parts, part 1, part 2, part 3, and also your final report. So that's I need to create an assignment on Canvas to do that. So that's not up yet, but that'll be up well in advance of it. Yeah. Any more questions on just the rest of what we have to go in this class? Okay. All right, so let's continue where we left off. So where we left off before, I guess before we took the midterm, was this idea of verification and validation, or what we call V and V. Right? Okay. Because if you use finite elements for in any kind of professional capacity or any kind of research, what you'll find is that the most difficult thing about using finite elements is not actually pushing in the buttons or not actually writing your reports. It's actually convincing people that what you find from finite elements is actually legit. And so the general response, especially when you're kind of first starting out, maybe you graduate and you get a job, is that everyone will think your finite element results are bullshit. And so the difficulty that you'll find is actually just convincing people that your results are actually reliable, and that's what verification and validation is, right? And so just a quick recap. Verification is a way to basically test to make sure that you're solving the equations correctly. Right? Oh, question in the chat. So so for the homework grade, is the total of the combined scores of the 6 assignments, or is each assignment equally weighted as the other? So each assignment that we've done so far has a point total, and I basically just took the average I basically just added up the point totals for all the assignments, and I divided by the total number of points. And so, I think the ANSYS activities were worth a little bit more. So I think those are worth 100 points. But the other homeworks, I think the amount of points it was worth was based on the number of questions that there were. Yeah. One thing that Canvas does is that it automatically drops your lowest homework assignment. And so whatever your lowest assignment was, it'll automatically drop that and calculate your grade on kind of whatever is left from that. Okay. And so verification, it's we're asking the question of whether we solve the equations correctly, right? Because anytime you run a finite element simulation, there's the underlying partial differential equation. So it could be like the heat equation. We've seen that one a lot. Or it could be like the linear elastostatics, right? So that's another equation. And so, when you ask a question of is this code verified, then you're saying, are we solving this equation correctly? And so on the other side of that is validation. And so validation is more of a question of not really the code itself, but more about your problem setup. Okay. And so what I mean by that is we want to make sure that what we find from our simulations is an accurate representation of reality, right? And so if we do a simulation on like a heated plate, you know, the temperatures that we find from our simulation, if we recreate that exact thing in real life, then we should find that we get the exact same temperatures there, okay? And so, you know, if you're using kind of an established code, so say like you're using ANSYS, right? A code that's going to cost you, you know, several thousands of dollars. Mostly what you're buying is you're buying a lot of the reliability, right? And so, you know, the reason ANSYS exists, you know, as a commercial software, the reason you pay for it is that the company has done a lot of this work for you. So they verified it, you know, to make sure that their equations are solved correctly, and they validated it against a lot of, you know, real life situations, real life experiments to make sure that, you know, the results are reliable. Okay. But even said that, even if you're using a commercial software like ANSYS, there's still some work that you have to do to make sure that your results are verified and validated. Okay. And so I think the thing that we left off on was this idea of a mesh convergence test, which is probably the #1 thing that you have to do for verification. And so the idea with mesh convergence tests is we want to basically make sure that our mesh is refined enough to get an accurate solution. Okay. Because we know that for a finite element problem, you know, your computed solution will depend on how many elements that you have, right? And generally what we expect is that the more elements that we put in, you know, the more accurate our solution is going to be, okay? Because you're going to run into a lot of cases where, you know, you do a finite element simulation, but your mesh is a little bit too coarse, or you don't have enough elements to get an accurate solution. Okay. And so, you know, when a lot of people see this, you know, and you're kind of using finite elements for the first time, I think the fair question is, why don't we just mesh it to oblivion? So why don't we just give it like 1 billion elements and then just call it a day, right? Because if we have 1 billion elements, you know, I think for almost any kind of problem, 1 billion elements is going to give you probably the most accuracy that you're ever going to ask for, right? But the problem with that is, as you increase the number of elements, so does your cost, right? And so, you know, if we think back to, you know, a lot of the finite element problems that we've tackled by hand, right? And so more elements means that we have more nodes in our mesh, right? More nodes means that our global stiffness system is going to have many more rows and many more columns, right? And so a lot of times you reach a certain point when the global system is just so big that it's impossible to kind of solve in any practical ways, right? And a lot of times these systems can get much larger than what you expect. And so even like a fairly modest mesh of, let's say maybe like 500,000, you know, let's say that you have 500,000 elements. You know, if depending on the type of problem that you're solving, so say like you're solving a fluid mechanics problem or you're solving a structural mechanics, you know, a mesh with 500,000 elements could have a matrix or a global linear system with literally like 5 million rows and columns. Because it blows up quite a bit, because at each node, you know, you're going to have multiple degrees of freedom. So it blows up. And so you want to be careful where, you know, you want to have your mesh fine enough so that you get an accurate solution, but not too fine that you're wasting kind of a lot of time and a lot of computational resources. So you kind of want to be in a sweet spot in between. And the way that you find that sweet spot is with a mesh convergence test. Okay, any questions on this? Okay. Okay. And so the reason I put this mesh convergence test under the category of verification is that any errors associated with mesh quality are purely numerical. Okay. So it has nothing to do with, the equations that you're solving. It's just, or the setup of the problem. It's just that, our mesh, it's just not fine enough to handle the equations that we want. Okay. And so when you're doing a mesh convergence test, basically what it means is that you're going to run your simulation multiple times with different mesh refinements. Okay? Okay. And so what do I mean by mesh refinement? So mesh refinement is kind of a term that we use to say, not only how many elements do we have in the mesh, but also what are the relative sizes of the elements. So mesh refinement can be defined in kind of one or two ways. Okay? And so the first way is defined as just simply just the number of elements that you have. And so, if you produce a mesh on a geometry, you can very easily quantify how many elements that you have, and the more elements that you have, generally the more refined your mesh is. And so the other way that we quantify mesh refinement is the size of the elements. Okay. And so meshes that have smaller elements are more refined. And so that's kind of another way to quantify that. And so when you're running a mesh convergence test, you're going to run, multiple simulations where oftentimes you're going to start with a fairly coarse mesh, and then you're going to reduce the size of the elements, which will increase the number of elements. And then from that, you should be able to produce a plot that looks like this. And so on the x-axis here, you have number of elements, and on the y-axis right here, you have some quantity of interest. Okay, and so your quantity of interest is oftentimes, what you're interested in solving for in your finite element simulation. So this could be like, say, if it's a structural simulation, this could be like a stress, or if it's a thermal simulation, it could be like it could be a temperature or a heat flux. For fluids, it could be like a pressure or wall shear stress. Okay, and so what you should find is that the graph should look something like this. Okay? And so let's say that you start right here, and so say that you ran your simulation at a very coarse number of elements, and so you have a very small amount, and your quantity of interest has some value right here. Okay, then as you refine the mesh, what you should see is that your quantity of interest is going to change value, until eventually you reach this point where it's if you refine the mesh anymore, then your quantity of interest is not going to change value. So you should kind of reach a plateau over here. Okay. And so once you reach a plateau, then what you can basically say is that once you basically reach let's say this point right here, then this result basically tells you that if you refine the mesh anymore, you don't get any additional benefit from it. So the accuracy doesn't go up anymore. So this mesh, this number of elements, or this mesh refinement right here, this is the perfect mesh for your job. Okay. And so if you run your analysis and you write and you do your, you find all your main results on that mesh, then you can use this graph to say that, you know, I don't have any errors that are associated with the mesh, or the mesh errors are minimized. Okay? And so this is almost a necessity. So anytime that you're using finite elements for any kind of, you know, professional or research capacity, this is a necessity, just to show that, you know, that your results are not changing with your mesh density, because that's always the #1 question that's always asked. You know, when people are looking at other people's simulation results, it said, is this result mesh independent, or did you run a mesh convergence test, right? And so no matter what you're doing with finite elements, this is something that you're always going to have to show, okay? Because it's the #1 source of errors, and it's the #1 rookie mistake that a lot of people make. Okay. Any questions on this? All right, so the question in the chat is, do you need to add extra code for this at the end of the project code and plot? So you don't have to write any additional code, but the only thing is you just have to run the code for differing element sizes. So I think at the very top of the code there should be a line that lets you specify the size of the element. And so once you're done kind of writing the code, I want you to run it with a fairly large size, and then just keep running the code over and over again, and give me a measure of, say, like the temperature. The maximum temperature in the plate, or, you know, I think explicitly in the project what I want you to show me is just the color contours of the temperature at 3 different mesh densities. So you don't have to write any additional code. You just have to run the code multiple times with different mesh sizes. Yep. Mm-hmm. Okay. And so I want to make one more comment on verification, just because it's relevant for you guys' projects. Is that I want you guys to really be careful, you know, first of all, if you're using your own code, code that you're writing, or if you're using open source or research software. So ones that, let's be honest, ones that you don't have to pay for, okay? Okay. And so that's not to say that, you know, open source code is unreliable. So there's a lot of really great open source projects that have a ton of support, you know, from government funding and other stuff. But you know, part of the reason why it's free is they don't have a big staff behind it supporting it. And so, you know, this kind of manifests in a couple ways. So first of all, you know, if you use open source code, you'll very quickly learn that the documentation for it is either non-existent, or if it's there, it's terrible. So it's really hard to learn. And second of all, you know, they haven't tested the code on a very wide range of test cases. So, you know, if you're going to use their code for something that's unique, you know, very often you're going to have to do a little bit of verification yourself. Okay. And so besides a mesh convergence test, another thing that you can do with open source code is to run what's called benchmark tests. Okay. And so benchmark tests are basically simple problems that you know the solution to. Okay. And so if you run the open source code on these benchmark tests, you should get the result that you expect. And if you don't, you know, there's probably something wrong with the code. Okay. Oh, question. So for the project, are we allowed to tweak number of lines in the code, or tweak in place where instruction says? Yes, yes, yes. So so if you notice in the starter code, I put some hints right there to say, you know, this should be 2 lines, 3 lines. And so you can, that's just a general guideline. So you don't have to do that in that number of lines. So I think for a lot of you guys, I think writing some more lines of code to kind of help with that, I think will be helpful. Or if you can do it in less number of lines, that's fine too. So that's not a requirement. That's just kind of just a helpful tip, just to kind of give you a sense of you know, of how many lines it took me for my solution. But it's not a requirement at all. Yeah. Okay. And so if you're using if you're writing your own code, if you're using an open source, make sure to take a few extra steps just to verify with some benchmark problems, just to kind of make sure, because I think that gives you some peace of mind too, just to tell you that this code is actually reliable. And oftentimes, when you run these benchmark tests, it'll help you kind of learn the code as well, because maybe you're setting something up incorrectly, or you're not setting a certain parameter correctly. And so doing these kind of benchmark tests will kind of help you also get familiar with the code as well. Okay, so that's verification. And so now let's move on to validation. And so validation, remember, the way that we defined it is validation is a way to show that what we get from our simulation results matches the corresponding situation in reality. Okay, because remember, we're simulating things to represent kind of reality as accurately as possible. So validation is a way to kind of basically assure people that what we get in our computer will match what we get in reality. Okay? And so there's several ways we can do validation depending on what's available to you. And so I'll kind of give you the kind of gold standard for validation right now, and that's either experimental measurements or real life measurements. Okay. Okay. And so the idea with this is that in order to validate your code, you would run a simulation, and then you would perform an experiment under the exact same conditions. Okay. And so if you do this and you properly measure the experimental results, what you should see is that you should get the same results. Okay. And this is kind of the gold standard, so that you can show that I've set up a simulation in ANSYS. I applied the boundary conditions, I meshed it, right, and I set up the exact same experiment in the lab, right. And if you measure the exact same quantities at the same locations, you should get the same thing. Okay. And so as an example, let's say that we wrote a finite element code to measure or to do beam bending. And so let's say that on the left right here, we have our experimental setup. Okay. And so let's say that we have a beam just like this. Okay. And let's say that we apply force. So we have basically a cantilever beam. Okay. And then on our experiment, we place a sensor right here. Okay. And then from that sensor, we can measure stress and strain. Okay. And then if we set up the exact same thing in simulation, okay, so let's say that this is like an ANSYS or something. Okay. So let's say we have our beam, but since we're finite elements, we've meshed it. Okay. And so let's say that we apply our force. Okay. And so if we run our simulation and we compute this, the stress and the strain right here, the computed stress and strain should be exactly the same thing, okay? Ideally, right? And so if you can do this and you can run and you can show that this is reliable, for all the different locations of the beam, then what you've just basically done is you've run a validation experiment and you've shown that the code is reliable for beam bending type problems. Okay. And so this is an important piece to any kind of code that you want to do any kind of professional work, because you want to make sure that your code is representing reality as closely as possible. Okay. Any questions on this? Okay. And so what happens if you don't get the same results? Okay. So if the results aren't the same, you need to check how you set up the problem. Okay. And so the main sources of errors most of the time are either choosing the equation to solve. Okay. And so that's the first thing. So say you picked a heat equation to solve for a structural problem. I know that's kind of an extreme example, but there's some other things, like if you're doing structural problems, there's linear structures, there's nonlinear structures, so you want to make sure you choose the right equation. Okay. And then the number two error is boundary conditions. All right, question in the chat, let's see. So with empirical analysis using same lab view, what's a typical convergence rate? Like within 15%. Yeah. So Chris is asking a question right now, is that, if you do run an experiment to validate your results, how close do your simulation results do they need to be to the experiment to say, that your results are validated? Right? That's a really good question, because, it's oftentimes, you're depending on your experimental setup and your simulations, you're almost never going to get them to match, on the dot. And actually, if they do match on the dot, then people might suspect that you're faking data or there's some kind of research fraud going on. So there's always going to be at least some little bit difference. And I think Chris threw a number out there called 15%. And so unfortunately, it's hard to give a hard and fast number for how close you should be. So I can't say that you should be within 10% or 5%, because it's going to depend. First of all, it's going to depend on the type of phenomenon that you're measuring. And so if you're doing something really complicated, it's like something multi-physics, like fluid structure interaction with combustion and chemical stuff, that's something really complicated. So I wouldn't expect something like that. They would expect you anything more than like 20%. 20% is kind of big. I would say you'd have to get within 10% for that. But if it's something that's relatively simple, like just a simple fluid flow or just a simple structural problem, with not that much physics going on, I would say you'd have to get within, at the very least, like 5%. And that's being a little bit conservative. So I think a lot of times they'd like to see it, within, 1 or 2%, I would say. Yeah. And of course, just like Chris kind of mentioned, it also depends on how accurately you can even measure that phenomenon to begin with too. So, validation is it sounds kind of boring, compared to a lot of other things you can do with finite elements. But I would say it's probably the most important thing, and it's one of the most difficult things to do as well, because you have to be really good not only with your simulations but also with your experiments. Yeah. So you have to have a very wide range of skills for that. Okay, and so among these two quantities that I have here, the boundary conditions is probably the most common mistake that people make, because boundary conditions, a lot of times it's difficult to specify the right boundary conditions on your simulation, because in reality, the conditions that you have there are very complex, and it's hard to kind of fit a complex real life condition to something that you can click from a menu in ANSYS. And so a lot of times, you're going to have to adjust your boundary conditions to make sure that they're perfectly accurate. But a lot of times you're not going to be able to find the perfect boundary condition too. So a lot of the game is kind of just kind of choosing what's the best boundary condition that you can choose for a given situation. Okay. So that's the gold standard for validation. But I will say that 99% of the time, unless you actually work for ANSYS or something, you're not going to be doing a validation experiment. Because after all, you know, the reason you run a simulation is to avoid doing a physical measurement to begin with, right? And so, you know, doing both an experiment and a simulation is extremely rare. Because if you're doing an experiment, it kind of defeats the purpose of doing a finite elements to begin with. So, and so how do you do validation, you know, without physical experiments or without physical, you know, measurements? Okay. And so one way that you can do this is you can validate against an experiment that has already been run in the past. Okay? Okay. And so if you look into the scientific literature, there's tons of papers out there on experiments that people have run on any kind of situation: pipe flow, airplanes, you know, heat transfer, structures. You know, there's all different kinds of experiments, and their results are very well documented in their papers. And so if you don't want to set up an experiment yourself, one thing that you can do is, if you're trying to validate a new code, is to try to mimic the results of their experiment. So you set up your simulation to be kind of have the same same setup as their experiment, and you try to recreate their experimental results. And so, you know, if just because you don't have the time or the money to run your own experiment, doesn't mean that you can't validate against an experiment that someone else has run. So I would say this is probably the most common way that people validate their codes, is that they look for a paper that ran an experiment that's similar to what they want to accomplish, and they try to recreate the exact same experimental results. So I would say this is kind of the most common thing. Okay? Another thing that you can do is that if if you're working for kind of a big engineering company, you can see if there's any kind of internal documents or internal measurements that you can take advantage of. Okay, and just like you know, a published paper, you can use those as well. Okay, because remember, the idea with validation is that you want to make sure that your code represents reality. So any kind of real life measurements on, you know, on a situation that's similar to what you want to accomplish, all of those can be used for validation. Okay, so if you can basically say that, you know, I have these experimental results, or I have these measurements, and they're taken from a reputable source, so they're either published in a scientific journal or they're done by a good group in your company. If you can recreate those results, that counts as validation. Okay. And so, you know, all these are great. So, you know, even though validation is typically done for codes that are being developed, you know, when you're first starting off with finite elements, these are kind of great to do in general. So kind of when you're first starting off and you're kind of you know, doing finite elements in your company or something like that, or for research, it's good to kind of do these kinds of tests just to kind of not only kind of get your feet wet, but also to kind of show people that, you know, you kind of know what you're doing with finite elements. Okay. Okay. And so what if you don't have any of these? So what if you don't have any kind of published experiment or any kind of internal measurements? Is there another way that you can do validation? And so the answer is yes. So this last method is not as reliable because it's not based on physical measurements, but it can at least perform a sanity check for you. Okay. Okay. And so one last thing that you can do in the absence of any kind of measurements and say that you can't do an experiment of your own is to just check your results against a simplified model. Okay? And so what I mean by simplified model is just any kind of analytical equation that you can solve by hand that's similar to something you can simulate. Okay? Oops. Not an experiment, in simulation. Okay. And so this could be, say that, say you set up a simple, ordinary differential equation, like a strong form of a problem, and you solve that by hand. If you can simulate that same thing in ANSYS and get the same results for the displacement, or for any kind of code that you're running, that's another way that you can validate your results. So it's, obviously for this method, you're going to be limited to very simple situations, but at least it's better than nothing. Okay. Okay. And so for your projects, the way I'm giving you something that's kind of built into the code to let you verify and validate your results. And so if you if you run the code, what you'll notice is that the very last figure that's produced, I think, is figure 6. Figure 6 is the exact solution to the problem, or not the exact solution, but it's MATLAB's solution to the problem. And so what you should be doing to check your work is that when you run your code, you should get the exact same results as figure 6, or the color contour should look the same, right? And so that's basically the way that I've kind of baked in verification and validation into your code for you. Okay? All right. So the question in the chat is: does non-dimensionalization in Buckingham Pi for model planes fall under this validation category, or would it be under full validation? Yeah, that's a good question, because a lot of times when you're checking against published research, a lot of times they present their results under using non-dimensional numbers, and which they've obtained from Buckingham Pi. And so you would probably use it most if you're designing your own experiment, and to say that you're going to write a publication or to show your results in an internal report. A lot of times you want to present these results using non-dimensional numbers. So Buckingham Pi would mostly come into play if you're designing your own experiments for validation. Yeah. All right. Any final questions on this before we move on to 3D element types? Okay, so that's verification and validation, or V&V, as what it's typically called. And so V&V is a really important step of the finite element process. Anytime you do finite elements, professionally or anything like that, you're going to have to do some V&V, at least to some capacity, just to show that your results are reliable. Okay? And so one of the most important things, to make sure that your results are accurate, is to choose the appropriate element types for your analysis. And so, I'm gonna, for 2D elements, we've gone over, triangles and rectangles, and so I'm not gonna spend any more time on that. But I'm gonna spend, most of today talking about 3D element types. These are the element types that you're going to be working with mostly if you're going to be using ANSYS or any kind of commercial software, because we live in a 3-dimensional world, And so, you know, if you're importing some geometry from a CAD software like SolidWorks, you know, you're going to be working with 3D geometries 99% of the time. So it's good to kind of focus on these. Okay. Okay. And so the motivation for this is that choosing appropriate element types is crucial to finite elements. Okay. And so when I say choosing right here, there's basically two choices that you kind of have to make. Besides the size, so you know, mesh size, that's another thing that you have to choose. But you know, we've already covered that with mesh convergence. And so when I say element types, what I mean is either you're going to choose the shape of the element, and you're going to choose the order of the shape functions. Okay. And so for shape, you know, that one's fairly obvious. And so that's that is going to depend on, you know, what kind of element shape that you want, right? And so in 2D, we've seen two different kinds of shapes. So we've done a lot of work with the rectangular element, and for the project, you're going to do triangular elements. So those are kind of the two main choices for that. And so for 3D elements, you know, your choices are kind of 3D versions of that. And so the 3D version of a triangle is known as a tetrahedron. And so it looks like this. And so if you play Dungeons and Dragons, this is basically your D4. And so a tetrahedron is basically a four-sided pyramid. Okay. And so you can see from my not so great drawing there that there's 4 nodes, and there's also 4 sides on this pyramid. So that's your first choice. Okay. Okay. And so your other choice of element is the formal name for it is a hexahedron, but the other name that people call it is a brick because it looks like a brick, right? So it's basically just a rectangular box. So I have to excuse my poor drawing, but you know, you guys know what a box looks like. Okay? And so a box has 6 sides and 8 nodes. Okay? Okay. And so you have a choice between these two, and they both have specific properties that we're going to go over today. Okay. And then the other thing that you have to choose is the shape function order. Okay? And so for shape function order, you often have 2 choices. Okay? The first choice that you can have is you can choose a linear shape function, okay? Or you can choose quadratic. Okay. And so remember, you know, we've worked with shape functions quite a bit, you know, over the last few weeks, and the order basically just means what kind of polynomial is it, okay? And so if you choose a linear shape function, what that basically says that you have linear functions that that you can use as an interpolation function on your element. Okay? And so linear is often the simplest and the cheapest. Okay? Okay. That's because you need less nodes for a linear element, which we'll go over in a bit. Okay. Or you can choose the element to be quadratic. Okay? And so quadratic is more expensive because you're going to have more nodes per element, but you get much more bang for your buck. Okay. And you know, the nice thing about using quadratic elements in like ANSYS is that ANSYS does all the really painful parts for you. So basically everything that you guys have been doing the last few weeks with like linear shape functions, getting element stiffness matrices and stuff like that, I will tell you that that process is 10 times more painful with quadratic elements, especially in 3D. And so the nice thing about using ANSYS is that they've done all that painful stuff for you. That's why you pay them, you know, a few $1,000s to use their software. And so the nice thing is that you get to get all the benefits from it without most of the downsides. And so what we're going to talk about today are, you know, what are some choices, or what are some ways that you can choose between these two options? Because, you know, if you combine these two, you have basically four different choices. So you can pick tetrahedron for shape, and you can pick a linear shape function. You can choose tetrahedron for shape and quadratic shape functions, and then the same thing for bricks. And so, you know, there's certain criteria that you can choose, that you should look out for to kind of help you make these decisions. Okay. Any questions on this? Okay. All right, so let's go over tetrahedrons first. And so the nice thing about tetrahedrons is that they're kind of the simplest possible elements for 3D finite elements. Okay. Another nice property that tetrahedrons have is that they have this what they call a simplex property. And so what the simplex property means is that you can use tetrahedrons to mesh any kind of 3D geometry. Okay. And so you can have the most complicated, weird geometry in the world, but you know, it doesn't matter for tetrahedrons, because tetrahedrons, they can just by how they're shaped, they can fill any geometry, and they can do it, you know, in a very efficient way. Okay. And so because of this property, you know, this is probably the nicest thing about tetrahedrons, is that if you know that your geometry is something that's really complex, or has a lot of curves and bends and stuff like that, you know, usually it's a good idea to start with tetrahedrons, because you know that you can get a mesh out of it. Okay. Because one thing that you'll see is that once you start using, you know, finite elements for complicated geometries, one step that you're going to be frustrated at is that it's a lot of times, you know, the mesher will fail for certain kinds of geometries. Okay? And so if you're getting that error a lot, you know, it might be a good idea to switch to TETs, because TETs will be a good, you know, TETs will give you a mesh most of the time. Okay. Depending on, you know, what other settings that you put as well. The downside of using tetrahedrons is that even though they can fill any volume because of the simplex property, they're not that efficient at doing so. Okay. And so what I mean by that is that if you have kind of a big space, you know, it'll be possible for tetrahedrons to fill that space, but it'll probably take a ton of tetrahedrons to do that. Right? And so let's say that we have a domain that's basically a giant cube. Okay. And so let's say that if we wanted, let's say that we wanted to mesh this giant cube with tetrahedrons. Okay? And so it can do it. So that won't be a problem. But what you'll end up with is a very large element count. And a lot of times, you know, that's something that you don't want, because, you know, the more we know that the more elements that we have, you know, the more difficult or the more costly our simulation is going to be. Okay, and so, you know, that's one thing to kind of keep in mind with tetrahedrons. So to kind of sum it up, you know, if tetrahedrons, they're the simplest element, and if you have a complicated geometry, you know, they're usually kind of one of your go-tos to do that. But just to kind of be aware that, you know, it might not be the most efficient mesh around. So a lot of times, if you can use hexahedrons for your mesh, you know, that's usually a better path to go. Okay. All right. Any questions on this? Okay. Okay. And so that brings us to hexahedrons. And so I will say that, you know, hexahedrons are generally more preferable if you can swing it, okay? Because they're a lot more efficient in terms of filling space, and so you can simulate a problem with hexahedrons much more efficiently than you could with tets. Okay. And so the reason it's more efficient is that hexahedrons have can be distorted a lot more than tetrahedrons. Okay. Okay. And so what I mean by that is that you can take a hexahedron. So let's say that we have one that looks like this, okay? And then, you know, say that in order to mesh it to a certain place, say that we need to squish it. So let's say that we need to produce a hex that looks like this. Okay. It turns out hexahedrons are much more okay with being squished like this, but tetrahedrons are not so much. Okay. And so if you have kind of a similar thing with tets, right? And you try to kind of squish it into a smaller space, you know, tets aren't going to be happy with that. So what the tet will do instead is that in order to fit into that smaller space, it'll just use more tets. Okay. And so this is not an accurate representation. Okay. But you get the idea. And so if you need to squeeze into kind of smaller spaces, you know, hexes are better than that, okay? And so where do hexes struggle? So hexes they struggle just from the fact that they're very kind of blocky, okay? And since they're so blocky, you know, they really struggle to mesh around curved geometries. Okay. And so if you have something that, if you have a geometry that has a lot of curves or has a lot of fillets and stuff like that, you know, it's going to be difficult for hexes to get into there because they're just kind of naturally very blocky. Okay. But I will say, so I'll be the first to admit that, you know, based on kind of my previous work, I haven't done a lot of work with hexahedral meshing because, you know, just because of the research that I've done, TETs are usually a lot more standard because I deal with a lot of kind of curved geometries. But you know, just from my experience of using hexes with ANSYS, I think hex meshers have come a really long way than they have in the past. And so, you know, at least with using ANSYS, the hex mesher is actually really, really good. Okay. And so a lot of these issues with going around curved geometries and stuff like that, actually ANSYS can actually handle those with hexes pretty well. And so, you know, for any kind of geometry, I would try to see if you can mesh it with hexes first, just because it's you'll get a higher quality solution then, and you'll end up with less elements. But if that fails, then you can go to TETs after that. But I haven't run into too many cases where hexes will fail. And so I think hex meshes have come a long way. And it would be great if ANSYS can take that code and share it with the world, but I'm sure that they've developed that for many years, and you know that's partially what they're selling. Because you know if I'm just thinking, you know, for a lot of problems, if for a lot of other codes, if you can use that hex mesher, it would help the code quite a bit. But you know the technology isn't there yet for a lot of situations. Yeah, for the right price, I think they would share it. But it's yeah, the right price isn't there for a lot of times. Okay, any questions on hex meshing? Okay, and so those are kind of the general characteristics that you would use to choose between TETs and hexes. And so let's talk about the choice between linear and quadratic elements. So we've kind of very briefly talked about quadratic elements for 1D, but basically what the upshot for that is if you're going to upgrade the shape functions, you need to include more nodes in your element to compensate. In other words, quadratic elements require more nodes per element. And so the TETs and the hexes that I drew on the previous pages, you know, those are for the linear cases. So for the linear 3D elements, you basically only have nodes at the corners of your element. Okay? But when you upgrade to quadratic, you need to add additional mid nodes at the middle of each edge. Okay? And so let's take the tetrahedron first. And so our tetrahedron looks something like that. And so we had four nodes. Okay. If we want to upgrade this to quadratic, we need to add additional nodes at the middles of each edge. Okay. And so we have an additional 6 nodes there. So our quadratic TET here has 10 nodes. And we can draw a similar expression for the quadratic hex. Okay. And so those are all the corner vertices. And then now we need to draw the mid nodes. Okay. Okay. And so in total, a quadratic hex will have 20 nodes. Okay. And so what does this mean for your analysis? So what this means is that if you're going to use quadratic shape functions, the cost per node is going to increase. And so the cost of basically, if you kind of compare just kind of apples to apples, say that you had 5 linear elements versus 5 quadratic elements, those 5 quadratic elements will be much more expensive than the 5 linear elements. Okay? But you know, by upgrading to quadratic, you actually get a lot of benefits as well. Okay? And so even though the cost is going to be higher, you know, the accuracy is also going to be higher. And so what that basically means is that if you're going to use quadratic elements, you can use less elements than you would have for the linear case and still get an accurate solution. Okay. Yes, yeah. So we're going to talk about that next, actually, too. So so TED's also shear lock, but Hex is also shear lock. So remember, shear locking is a function of the shape function order, not the shape. Yeah. But yeah, we'll cover that on the next page. All right. Are there any questions on this? Okay. All right, so Chris brought up a really good point, which is something that's specific to only structural finite elements, and that's this idea of shear locking. Okay. So shear locking, this is a phenomenon only unique to physical or to structural finite elements. Okay. And what happens is that if you use linear shape functions for a structural problem, what can happen sometimes is that the structure can kind of lock on itself and it looks really stiff. Okay. And so, you know, what tends to happen is that for linear shape functions, the displacements or the deformations are grossly underestimated. Okay. And so what this basically means is that if you're going to be doing a structural kind of finite element simulation, most of the time you're going to use a quadratic element. Okay. And so that's something that's unique to structural FEA. So I wanted to make sure I mentioned that because it's I know a lot of you guys are going to be using finite elements professionally for structure, because that's kind of one of the main applications. So that's one thing to kind of look out for. Okay? But if you're using FEA for like heat transfer or for fluids, linear shape functions are actually more common for that, and that's actually what you're doing for your project too. And so for your project, you're using linear shape functions, and you're using for heat transfer problems. We don't have to worry about the shear locking thing at all. Okay. And so now that we've kind of gone over kind of the basic characteristics of, you know, linear and quadratic and tets versus hexes, you know, I think kind of the fair question to ask right now is that it's, you know, it kind of makes the choice seem a little bit more complicated, right? And so, you know, I think especially between linear and quadratic, because even though quadratic elements are more expensive, you know, you need less of them to get an accurate solution. But then that kind of begs the question of how much less do you use, right? And so do you choose to run a simulation with a lot of linear finite elements, or do you choose to run a simulation with less quadratic elements, right? So a lot of times that choice isn't really clear. And unfortunately, you know, that's kind of where I have to leave the discussion, because it's there's no hard and fast rule to choose, you know, which path to take, unless you have something like shear locking to kind of help you choose for you. Okay? And so that's why, you know, I spent a lot of time earlier this lecture talking about the mesh convergence. And so no matter what you pick, for if you pick linear shape functions or quadratics or tets and hexes, you know, you're going to always want to do a mesh convergence test to basically show that your mesh is reliable for your simulation. Okay? And so in the notes, I do have a table, which I do want to share with you. So let me go ahead and share my laptop screen. Okay. And so this table here is just taken directly in the notes. So these are in lecture notes 14 for 3D finite elements. And this table will kind of help you decide, you know, these are some heuristics that you can use to choose, you know, what type of element that you want to use, right? And so I've kind of grouped triangles and tets together in the same category, and also quadrilaterals, which are rectangles, and hexahedra, those are kind of in the same category as well. Okay? And so if you have any questions on, you know, what type of mesh or what type of element should you use for a certain kind of analysis, you can refer to this table, you know, and this kind of sums it up pretty well for the you know, for what you should what you can use. Okay. And so that's this table. Okay. Right. And so this down here basically shows you that if you do end up using quadratic elements, you need less elements in order to get an accurate solution. Okay. And so this is kind of just a very simple example. So let's say that you have a rectangular geometry here. And so in order to get an accurate solution with linear finite elements, you might have to mesh it to death, you know, like this, and put a ton of elements. But for quadratic, you know, you would only require maybe something that looks like this in order to get an accurate solution. Okay. And so, you know, just like I kind of mentioned, there's no hard rules for, you know, how you should mesh an element, for how you should mesh a geometry. You know, there's so many different factors that go into play. Right, so the only way to really know for sure is to run a mesh convergence test, because it's going to be dependent not only on the type of physics that you're running, but also, you know, what your goals for the analysis are as well. Okay. Okay. And so, you know, there's one last topic here for meshing, but I think, you know, that kind of goes together with the ANSYS activity that we're going to do on Wednesday. So I'll leave it for then. So let me go back to this table in case people want to write it down. So are there any final questions on 3D element types? Okay, so there's no more questions. That's all I had planned for today. And so remember, on Wednesday, we're going to be doing an ANSYS demonstration. So, you know, we're going to be doing another activity, but you're not going to be required to turn it in, because, you know, remember what I said at the beginning, that the project's going to be a lot of work. So I want to make sure I give you guys all the time and kind of the mental energy to tackle that on, because I want you guys to, you know, really work hard on that. So there's going to be no more assignments for the class. So what we do on Wednesday is just going to be just for your own information, and it's a pretty important topic too, because it kind of goes along this theme of proper element selection. Okay? And so I'll see everyone on Wednesday, and hope everyone has a good evening today. So thanks for tuning in. Project is due on the 21st. And so that's the Monday after finals week. So we'll be doing on the 21st, December 21st at 11:59 p.m. Thanks. Have a good night. Thanks, Ariel.